Given the functions f and g, find the f composed with g function. As a reminder, f composed with g of x is determined by taking the g function and plugging it into the f function. Since f is on the left of the composition notation, that is the function on the outside, and we'll begin by writing down our f function, but with a hole for that independent variable x, because what we'll do is plug the g of x function into that spot. But of course we use what g of x actually is, which is x plus 4 over 2x minus 5. And now we need to simplify this because this is what we call a complex fraction, which means basically that it just has more than 2 levels. We can't leave our answer as a complex fraction, so we need to simplify it. And when simplifying a function with functional notation on one side, we are limited to working entirely on the right-hand side. We can't do anything to both sides of this equation. We do not want to mess up the functional notation on the left, so we have to simplify this function by operating only on the right-hand side, which of course limits our options. One thing that we can do is multiply the top and the bottom by the least common denominator of all the fractions within the complex fraction. Remember, anytime we multiply by 1, it does not change the value of the function, but a well-chosen one will change the form. And the one that we choose is the least common denominator, which is 2x minus 5, because that's the only denominator in any of the fractions. So we'll multiply by 2x minus 5 over 2x minus 5, but it's actually a little bit easier to see if we drop 1s underneath these 2x minus 5s, so that it's easier to see what cancels when we distribute it into that numerator and what cancels when we distribute it into the denominator. So again, we'll copy-paste our functional notation on the left-hand side. Just to re-emphasize that we are not doing anything to the left-hand side, we're going to distribute this LCD into the first term of the numerator. Now just off to the side here, I want to bring your attention to the fact that what we're doing is we're taking 2 over 1 times x plus 4 over 2x minus 5 and multiplying that by 2x minus 5 over 1. The 2x minus 5s are going to cancel, and what will remain is the 2 times the x plus 4. And that's going to be what we have in this first position in the numerator. And then we multiply 2x minus 5 times negative 1, which is going to be negative 1 times, so we don't need to actually write the 1, 2x minus 5. And let's wait to distribute that in because of how much is going on right here. Then we'll take 2x minus 5 and multiply it into this first term of the denominator. And let's just take a close look at that multiplication. Basically, we have 2x minus 5 times x plus 4 over 2x minus 5, and those 2x minus 5s are going to cancel, leaving just x plus 4 in this position. And finally, we have minus 2 times 2x minus 5. Now we're ready to distribute and combine like terms. So we'll distribute in the 2 to get 2x plus 8. Now let's distribute in the negative to get minus 2x plus 10. We'll copy paste the x plus 4 because nothing was to be distributed in there. And then we'll distribute in the negative 2 to get minus 4x plus 10. So we have plus 2x and minus 2x, which cancel out. And 8 plus 10 is 18 in the numerator. In the denominator, we have x minus 4x, which is negative 3x. And then 4 plus 10, which is 14. And so this is our simplified version of the composite function f composed with g. In part B here, I've brought down the composite function. I'm now calling it 18 over 14 minus 3x, which is of course the same thing. And we're also looking at the f function and the g function because we're going to need those in order to find the domain of this composite function. Now let's just notice that there is one domain restriction that is pretty obvious from the beginning, and that's the fact that the denominator, 14 minus 3x, cannot be equal to 0. So who is the x value that causes that to happen? We'll set it equal to 0 and then solve for x, so we're going to get that x cannot be equal to 14/3. And let's just hold on to that for a moment and walk through our process of finding the domain of the composite function. Because while this is going to be a domain restriction, it's not the only domain restriction. And that's what makes the domain of a composite function a little more challenging. There's another domain restriction that we need to go and find. So let's just be reminded that the domain of a composite function is found by a two-step process. First, we have to find the domain of the inside function. Remember, any potential domain element has to pass through the g function first. So it has to be an allowable input for g, which means that it has to pass through g and generate a defined and real number. The domain of the composite function can't be any larger than the domain of g. So back up here, our first step is to find the domain of the g of x function. Well, this is our g of x function, and a rational function is going to have a domain restriction whenever the denominator of the fraction is equal to 0. So we set the denominator equal to 0 and figure out who is the x that makes that happen, and that value would then be the domain restriction. So we say 2x is equal to 5, divide both sides by 2 to get x is equal to 5 halves. And so let's make a note here that x cannot be equal to 5 halves. 5 halves would cause the output of g to be undefined, and undefined cannot be plugged into f. And so the second step for finding the domain of a composite function is to essentially set g equal to the domain restriction of f and then exclude any values that cause this to happen. Exclude any x value that passes through g to become the domain restriction of f. So we'll set our g of x function equal to the domain restriction of f. The only x value that we're not allowed to plug into f is 2, and so we want to figure out who is the x value that would cause the output of g to be the domain restriction of f, or the value that cannot go into f. We solve for x in this equation, and then that value will be additionally excluded. So this is a rational equation that's solved by multiplying both sides by the LCD. And the LCD in this case is 2x minus 5. So 2x minus 5 over here on the left, the LCD is going to cancel with this 2x minus 5, and we are left with x plus 4. And then multiplying the LCD over here on the right, we get 4x minus 10 after we distribute in that 2. To solve for x, let's get our x terms together and our constants together. So on the left-hand side, we have 14. On the right-hand side, we have 3x. And when we divide both sides by 3, what we end up with is x is equal to 14 thirds. So 14 thirds is the additional exclusion that we get when we set the inside function equal to the domain restriction of f. However, notice this additional restriction is the same as the one that we could see at the beginning. When we found the f composed with g function, it was pretty obvious that 14 thirds was a domain restriction. The one that wasn't obvious is that 5 halves was also a domain restriction. So to summarize, the domain of a composite function is found by a two-step process. First, we have to find the domain of the inside function. This is the domain restriction that is not obvious from the beginning. Then we set the inside function equal to the domain restriction of f, and what we end up with as an additional restriction is one that we could see at the beginning. We take these two restrictions together to come up with the domain of the composite function in interval notation, which is to start at negative infinity, and the first restriction that we get to is 5 halves. We'll leave out 5 halves and then go to 14 thirds. We have to also leave out 14 thirds and then finish out at positive infinity. And so this is our final answer for the domain of this composite function.